So we are celebrating now the 6th graduation ceremony, 2019-2020, of the Masters in High Performance Computing. And this coursework is driven by challenging scientific and technical problems which require high performance computational approach. And lectures are provided by SISSA and ICTP staff and highly recognized international experts. And both of us, the sister organizations, we have long histories and experience in developing and applying scientific and research computational models. So each year ICTP offers scholarships for applicants from less advantaged countries. And thanks to this support, 17 students from 13 countries have completed this program since its inception in 2014. So today I'm very happy to congratulate all the 14 students who are graduating today, and in particular the 3 students supported by ICTP from Philippines, Iran and Algeria. So Krister Jazz Urog is from the Philippines, contributing to a project on novel methods to model large-scale data analysis and biological data in collaboration with Professor Guido Sanguinetti, SISSA. Saeed Alei from Iran, who graduated with a project of porting a numerical model based on multi-component lattice Boltzmann and hybrid multi-GPU distributed systems. This was in collaboration with Professor Toski and the Technological University of Eindhoven. And then finally, Nasrine Yousfi from Algeria, who graduated with a project on the detection of recurrent behaviors on real banking data. This was in collaboration with Dr. Giacomo Sana from Prometei. It's a leading Italian company for consulting, software, and research. So all the best, and okay, I give the floor back to Luca.
So thank you very much. And now I would like to welcome. I would like to welcome on stage Professor Stefano Ruffo from the director of SISSA at the moment. So thank you very much, Stefano, for accepting to give us a short greetings from SISSA.
Thank you, Luca. Since Atish has already given many details about the program of this year, I will concentrate on other aspects. So first of all, I would like to thank the regional government for the support that is given annually to the master, and also the several companies that had signed contracts with SISSA to support the students with grants. In fact, this master has a double value, both in advanced numerical simulation for basic and fundamental research, and also for the development of skillness for the innovation of companies. So this double value is very much recognized by our funders. And also I would like to stress the fact that this is part of a strategy of the region, of which SISSA and ICTP are part in the high performance computing. And I would like to remind that high performance computing is central in many of the activities of SISSA, and is certainly transversal to both the areas of physics and mathematics, and that there are important research going on in condensed matter, in biophysics, in applied mathematics, and that all are part of the activities of the master. And I see more and more a very good blend of the different activities of research activity of SISSA in the topics of the students of the master. Moreover, as you know, SISSA has created a new group in data science, and I see that already there is a sign of these activities also in the master. So the master has reacted quite quickly to the creation of this new group. And that's all, and I will stay here to listen to the rest of the ceremony as far as I will be able to, and I welcome the next speakers.
Okay. So then, just to give you a very short overview of what's going to happen next, I'm going to give a short presentation of the master that is a presentation they usually give to just give an idea what are the numbers of the current edition with respect to the numbers of the full editions of the Master in High Performance Computing. And at the end of this very short presentation, I would like to welcome on the stage Professor Guido Sanguinetti. But before we do that, I would also like to ask all the students of the Master in High Performance Computing of the 6th edition that are present to switch on their camera so that we actually take a collective picture. It's going to just be a virtual group picture, but hopefully this will be changing in the near future. So what is the master? Well, the Master in High Performance Computing, for those of you who are new to this type of technology, is a innovative master. Well, it's an innovative program, so specialization program, training program, co-organized by SISSA-ICTP. And the main strength of this program are the connections with the institutions and companies, both regional institutions and regional companies, and international institutions, international companies. So SISSA and ICTP are lucky to live in, to be placed in a fantastic place, which is Trieste. Trieste has 30 research centers and high training centers, and this is about 30. And this is a incredibly good ground to get incredible ideas and to get incredible projects going on. And SISSA and ICTP also hold one of the Tier 1 clusters, one of the bigger clusters, computing clusters in Italy that is used, well, actually, we don't compete with Cineka, of course, those are Tier 0 clusters, but we have one of the largest ones for institutions. And this is a toy ground for our students, which is very much appreciated by all of our students. Even if sometimes it doesn't work exactly as it should be, but this is of course due to technologies that is always an issue with everybody. So just to give you some numbers of the Master in High Performance Computing, so far we've had 7 editions. We've had almost 100 students. There's about 95 students, 97, between 95 and 97. I have to be precise according to how many people are living and staying in the master or postponing their graduation of the master. The nice thing about the master is that with respect to similar areas of this high technology centers, the number of women that we have had so far is very large. So 20% is an incredibly large proportion. We hope to increase this number even more, but compared to similar fields and compared to similar situations around the globe, this is one of our strengths in a certain sense. 85% of our students had a scholarship, either from ICTP, from SISSA, or from sponsoring institutions or from sponsored companies, and 94% of our alumni are working at the moment. So 66% in industry and 34% in academia. So how is the master working? So the master is a 1-year program, which is very condensated and very centered in high performance computing and application of high performance computing. And it's split in 3 parts. So the first part is about 6 months, and we give the basic grounds for high performance computing and for programming to all of our students. And the second and third part usually happen at the same time. And in the second part, students start to understand exactly what they like and what they don't like. So for example, artificial intelligence, or maybe scientific computing, or maybe I don't know, there's many applications of high performance computing. So most of them in the second part would follow algorithms that are specific to their fields of expertise or to their fields of likeliness. And the third part, instead of thesis projects, which last from 6 to 9 months. And this second and third part are the ones that usually attract most of our sponsors, most of our companies, the companies that actually believed in the Master in High Performance Computing. Here is just a snapshot of the recent ones. And I am very grateful to them because they made it possible for the Master to be such a successful program so far, and also because a lot of these companies and a lot of these institutions and a lot of these research centers have come up with problems that were extremely interesting and pushed forward both the master towards the right path and the research that's been done in the master. So I think this has been a very interesting and a very powerful thing to do. And this is done thanks to our sponsors, as I just said. And of course, if you're interested, please contact me at the end. And we have a name for this, which is called TIP for HPC Fellowships, which is training and innovation program for HPC. And it's one of the best way to improve the projects that your companies may have, or to make your company HPC ready or ready for the next generation of problems. Nice thing about this year is that we have also a fantastic new website, which has just been put online, and we still have to fix a few things here and there, a few glitches here and there, but we have changed our logo. So we go from the logo on the top that you see here on the right to the logo that we have here on the bottom, and the new website hopefully will be much easier to navigate and much easier to follow, both for the students and for industries and collaborations and research centers that are interested to collaborate with the Master in High Performance Computing. So thank you very much for being with me. And now I would like to ask all the students to open up the webcam and to join with this group picture before I give the floor to Professor Guido Sanguinetti for his lectio magistralis. And I think this lecture, the magistralis, will be very, very interesting. So please, students, can you turn on your camera? Okay, thank you. Oh, I'm still missing somebody. Okay, let's see. Okay. How many are we missing yet? So let me just count. It's difficult. Okay, so everybody say cheese or something like that, and I'll try to make a nice picture of this. Okay. Thank you very much. I'll share this on the web page, and now it is my pleasure to introduce Professor Guido Sanguinetti. So Professor Guido Sanguinetti is an applied physics professor. He's currently the chair of data science at the National School of Advanced Studies in Trieste, and his background is physics at the University of Genoa, and he has had a PhD in mathematics at the University of Oxford. And I understood just a couple of days ago that after the PhD in mathematics is offered up, and he started playing music for a couple of years. I didn't know about that, about Guido, and now that I've learned about it, I also understand why listening to his talks is so musical and so beautiful. So he's been lecturer and then reader, and now he's, I'm very happy that we now have him at SISSA, and he will talk about the difficult dialogue between models and data science and artificial intelligence, and this is hopefully going to be a very nice lectio magistralis, and please welcome Guido Sanguinetti.
Thank you very much, Luca. Let's see if I can manage to share the screen. Looks like I can. Yes, indeed. And yeah, I'm extremely honored to do this lectio magistralis. It's the very first time I'm actually asked to do an event in Latin. So this is particularly challenging and fun. So thank you very much, Luca. I also have to thank Luca for giving me an extremely precise brief for my talk, like just say whatever you want. So, you know, I hope that what I have to say is not too tedious to you all. And unfortunately, I still have to get used to the fact that if you make a joke in an online talk, you can't hear anybody laugh. So, you know, I'll have to live with that. Now, difficult dialogue of models and data. And I realized that this might not be, I might not be the first person to talk about these things. And in fact, this is a painting, a very famous painting in the Musei Vaticani by Raffaello Sanzio called La Scuola d'Atene, And in the middle here, we have good old Plato that points upward. You should abstract and think of ideas. And his young disciple Aristotle that points downwards and say, no, you look at what's happening and you should base your philosophies on the observations of nature. And so I think it's really true that this dilemma between abstraction and ideas and reasoning and models and observations has been with us for a very long time and has been one of the critical divides in how we appreciate the world from a scientist point of view, at least. But I think the times are ripe to think about these things again, also in a more technical context. And why is that? Because really in the last few years, we've witnessed, well, maybe the greatest phase transition of all the world. If we think about a timeline of data, you know, for billions of years, there was obviously no data, there was no concept of data. But then humans started observing things, but for thousands of years, there was essentially no data. You know, there were a few sparse observations here and there. And now suddenly, for the last 10 years, there is too much data. So we've gone from having virtually very, very few capabilities to observe the world to having, well, I mean, obviously, in the context of what we had before, a very, very large amount of observations to make sense of. So I think this is what is at the basis, and I mean, it is not an original thought, this is what is at the basis of the new data science or AI revolution. The fact that we finally have a lot of data, and this is requiring, in fact, we are proceeding in an engineering fashion as humans have always done. So I think humans do things, then mess up, and then try to fix the mess later. Yeah? So here we're proceeding in the same way. So we are trying to do something with the data, and we'll see how it goes. So I think in this context, it's useful to take a little step back in these occasions for, you know, lectio magistralis type things, and think about whether what we're doing makes much sense, or how we could improve, or what are the big problems. So that's what I'm going to try to do from my very modest perspective. My plan is to start by introducing a little bit what I mean by machine learning. And I will be, the only equations in the talk will come in this section here. And I'll try to make clear that machine learning is probably a very useful thing, but it's not a very easy thing to do properly. And in fact, I think by and large, we have witnessed so far the existence of a few shortcuts to try to do it approximately. One that is the old shortcut, I call it the old shortcut, and then the new shortcut. And I'll try to discuss the two shortcuts and why they have some shortcomings. But the shortcomings of the modern shortcut, which is what we call AI, are what is of particular relevance. And I'll try to spend a little bit more time on discussing why these are important in my point of view. Also because that leads me directly to talk a little bit about what is the current research at SISSA, at least, and of course at SISSA and in collaboration with ICTP and other realities nearby, because I think a large fraction of the current research at SISSA in this topic is really about the big challenges. So what is machine learning? Okay, so if you go to Wikipedia, at least a few years ago when I first started presenting talks like this, it gives you a very dry definition as a subfield of computer science, and I think we probably could agree on that. It gives computers the ability to learn without being programmed. Now, me and my students and my postdocs, you know, we spend quite a bit of time programming, so we think we do machine learning, so we're not yet seeing these computers that don't need to be programmed. But it's certainly true that maybe it's not programming explicitly every step. Some of the steps have to be learned from data. So my personal definition would be more that, you know, machine learning is really a broad class of algorithms that represent mathematical patterns which are seen within data and fit these patterns to the data to some extent. It's you know, as much as an engineering discipline as it is a science, as it is an art, and you have to, as usual, kind of balance human input, which take the form of models, surprise, surprise, and data. And it's not so easy to know how to balance one and the other. It's greatly founded on statistics and optimization, and of course, it only works if we have very powerful computers, and that's where the HPC angle is particularly dominant. Needless to say, it turns out to be a useful thing to do when we have large and high-dimensional data sets. But this is still a very vague definition, yeah? Mathematical patterns within data. So what do I mean by that? Okay, so to try to be more precise, we start with a world, which is a system that we want to model, and we make, of course, some assumptions that there are some variables that pertain to this, to describe the state of this system. Yeah, we will think that they are random variables because we've all lived enough to understand that the world is random, and we shall say that we have some of these variables that can be observed. Let's call them Y. Other variables that cannot be observed, but we know that they should be there and they should be relevant. And to me, a model, by definition of model, is a probabilistic relationship between all of these random variables. So it's a joint probability distribution, if you wish. Typically, it is quite convenient because some of these variables are special because you can observe them, to split this joint probability distribution using the product law as the probability on the bits of the system that you cannot observe, then this can only be what your prior beliefs are about this part of the system. And also the conditional part that says, you know, if the unobserved variables take these values, well, what is the probability of taking these observations? Now, these two things have got a special name. They're called the prior, that's the distribution on what you've not seen before, exactly because comes prior to seeing something, and the likelihood. It's called the likelihood function, and it is a function of the state of the unobserved variables. And then machine learning or statistical learning, if you wish, has these general goals. Yeah, the first one is to learn this probability distribution, this joint probability distribution from the observations. So tune any parameters that may be in this probability distribution. And once you've done that, you can use Bayes' theorem to update your belief on the unobserved parts of the world. So I have a model, I have some prior beliefs, then I see some observations, and these observations are informative, provided that the observed variables are not independent of the unobserved variables. These observations will be informative and will allow me to update my belief on the unobserved variables. And once I've done that, I can even predict new observations. How do I do that? Well, I'll show you in a sec. So what do I mean by learning the joint probability distribution? Well, as I said, there will be typically some parameters, so I may be able to specify some functional forms of how the dependencies work, but these will have some spare parameters. And I will fit them by an optimization procedure, typically maximizing the so-called evidence, which is what is the probability of the observations if I average out the bits of the system that I cannot observe. The posterior inference is used by Bayes' theorem, which is recapitulated here. And the prediction is the most interesting part. The prediction is telling me, how would I do prediction? Well, my existing old observations enable me to have an updated belief on what the state of the system is. Now, conditional on this one particular value of the state of the system, I would be able to predict observations coming out of that state. So what I'm going to do, I'm going to use the posterior to average the state of the unobserved variables, and this will give me the average prediction for a new data, given that I've seen previous data. So this is what is called Bayesian model averaging, because I'm averaging the model under the measure that I have inferred from the previous variables. Now, unfortunately, this is extremely hard. This is the so-called empirical Bayesian approach. It's empirical because I do some optimization to fix some parameters, essentially. And the trick is that you know, I have to do these integrals. And these integrals are really computationally intractable. You know, we can have the best HPC in the world, but if, you know, to take a simple example, my unobserved variables are the spins of, you know, the state of the spin of 1,000 particles, well, you know, that's 2 to the 1,000. So it's a very, very large sum. And it's easy to find many more complicated systems. So it's really hard. And you need to do computationally tricks to find high dimensional integrals. And sometimes you can't even evaluate the likelihood because it's only given to you in an implicit form and so on and so forth. So there's a lot of research going into devising better algorithms to solve this problem in its generality. And it's really worth doing because, you know, you can accommodate all the uncertainties that you may wish to account for. You know, you may really give not only point predictions, you give full distributional predictions. You can say what are the ranges of confidence and so on and so forth. And all these things are really important, both in scientific domain, but also in many applications. But unfortunately, it is very hard. And so people have been looking for shortcuts. And they have been looking for shortcuts down the ages. So let's see a couple of these shortcuts. Yeah. So the first shortcut is the historical shortcut. And the historical shortcut is that there was never enough data. There was never any data, really. So what we could do, you know, we could take the few very sparse observations and abstract. And that was Plato's point of view. Now, as we know very well these days, you know, humans are very, very good at coming up. Unfortunately, most of them are completely wrong. And you just have to go through the web and find your favorite conspiracy theory to see that what that is just an abstraction of the world that makes no sense. Now, the great innovation of Galileo was really to say, okay, use your limited data and then target your resources in order to provide tests. So only explanations that pass the test of the data will have the strength to go forward. And this was really kind of, you know, a super idea, because if you think about it, it shifted the role of the scientist. So the scientist in the times of Galileo was still a natural philosopher, someone that tried to interpret the world. And after Galileo, he wasn't someone that tried to interpret the world, he was someone that was trying to predict the world and was staking his credibility on, or her credibility, on being able to give the right answer. So this, I think, it's probably been the best idea in the history of humanity, at least under some metric. And it's really been the origin of all of what our society prides itself on, being able to rationalize the world and test predictions and so on. And once, you know, we've also seen that this process can be incredibly powerful. You know, you can abstract and test very basic components, say on the biochemistry of proteins, and then do molecular dynamics and predict really, really difficult things. Or you can abstract properties of fluids and do computational fluid dynamics and predict, you know, the flow of water by a ship. Now, obviously, all of this has become incredibly powerful thanks to computers in the last few years. You couldn't do molecular dynamic simulations on a, you know, on a wooden computer in the 18th century. But it has served us extremely well. However, there is a problem, and I think there are several problems actually also with this purely abstract-driven point of view. Now, the first thing is that the data really has, you know, you could say has the central role of falsifying theories, but does not explicitly play a role in creating theories. It's got an ancillary role. And that has caused, you know, some anthropological problems as well. You know, I report here a couple of quotations from very famous physicists, which with the characteristic modesty of physicists, put data in its place. You know, data, yeah, fine, you do your observations, but the real science is not that. And I mean, I'm being controversial here, and I hope all of these chat things that I see here are not people being very angry to me. But I think there has been historically a very strong bias against the empirical and towards the theoretical within science. But I think there is also a genuine conceptual difficulty, which once you start having systems that are intrinsically complex and have intrinsically several parameters, need several parameters, then it's very hard to design the killer experiment, because you can design the killer experiment for a particular set of parameters, but if you don't know what those parameters are, it's hard. You know, John von Neumann famously said, give me 4 parameters, I will fit an elephant, and give me 5 and I will make it wiggle its tail. That's the, you know, that was probably interpreted as you should not over-parameterize models, but was also a cry for help that was basically saying the framework that we have is not suited to deal with models that intrinsically need many parameters. And I think if you want to model really complex phenomena, like the brain, how it functions and so on, you know, you just can't do it with 2 parameters. That's the way it is. Okay, so that was the old shortcut, let's say. What about the new shortcut? Well, the new shortcut has emerged recently because now we have data. And people have started to say, well, you know, we've got lots of data. Do we really need all these superstructure of models and so on and so forth? Well, maybe not. Maybe we can just learn the marginal distribution of the observables. Okay, so not worry about what underlies the data, just learn the data distribution. And that's what they do, for example, with generative models in machine learning. You learn the data distribution. Even better, in many cases that are of interest, you're interested in predictions, for example, in industrial predictions and so on. And then you just have to learn the conditional distribution of output with input. They're both data, but you just have to learn this discriminative prediction. That's a function. You ignore your uncertainty and you just learn a function by optimization. How well you tune the parameters, and it turns out that with modern HPC, you can do it very well using GPUs. So this is the function approximation view of machine learning. Everything is a function, collect enough data and we'll be able to reconstruct the function. And now if that sounds like join the dots, well, it is like join the dots. You know, you take millions and millions of data points and you interpolate between them. Pretty much, that's what's going on. It's been amazingly successful. However, I think there are some real problems with a purely function approximation driven approach to machine learning. And this is what I want to tell you briefly about. The main problem comes out of the fact that the function approximation view takes the data as the end-to-end aim of our life. So we just want to learn end-to-end a map from input to output. We don't care what this map is. And it turns out that the efficient way to do that is to stack multiple nonlinear functions, one on top of the other, with very, very limited input into how you design these nonlinear functions and how you stack them from humans. And conversely, very limited understanding of how the predictions happen. Now, is this a problem? Well, maybe. So let's have, I think not all predictions are equal. Yeah? Let's have a thought experiment where we have an Alexa type computer that we ask things and it gives us answers. And the first answer is we show it an image and it says, well, this image contains a cat sitting on a table. Well, maybe fine. Or we ask it to translate something and it tells us that good morning is the same thing as buongiorno or guten Morgen. Or we ask it a more personal question like, you know, what is my residual life? And it says, well, I've looked at your genetics and your lifestyle and you can expect another 20 years, 5 months and 3 days. Now, I think you will all agree with me that these 3 predictions are not the same. Yeah, and they're not the same conceptually from the point of view of how the user will receive such a prediction. Yeah? And the real issue is that, you know, if a computer or anyone tells me that I have this amount of life, I want to know, well, really exactly 3 days, or, you know, do you think it's going to be 7 days, or maybe it's going to be 28 years or whatever. So we don't have a measure of uncertainty on the predictions. And crucially, we don't know how the prediction has been reached. Because maybe I could, if I knew, I could find out that, you know, if I stop eating ham sandwiches every day, maybe I will live an extra year. Or if I stop drinking grappa in the evening, I will live an extra 3 years. And that is kind of relevant when the prediction really has an aspect like that it really affects the life of people. But there is a third aspect here that is important. I have absolutely no way of verifying whether the prediction on my lifespan is correct. I just have to wait 20 years, 5 months, and 3 days. And if I turn out to be still alive in the evening, I can say, well, it was wrong. That's not very helpful. While the other two examples, I can just check very easily whether it's correct. So I think we need to start thinking a little bit about these explaining predictions. And we really have to think about, I think, 3 key questions. Yeah, one of them is, does the decision affect the life of someone, or does have an importance in a certain way? Can it be easily verified? So can I just check whether it's right or not? Because if I can just check, well, then, you know, it may be economically more expedient to have a computer do the prediction, but it can always be verified, and I can check analytically or, you know, empirically how accurate the computer is. And finally, can I act to change the prediction? Because if I can act, I need to know which action I need to take. And for that, I need a reason why a certain prediction was made. And so I think in these cases, you know, depending on the answers to these 3 questions, one may or may not really need both a robust explanation and a quantification of the uncertainty associated with the predictions. And this is a massive mathematical challenge, because it really forces us either to figure out how to look into the black box, or to completely rethink the strategy that has been used so far in AI with so much success. But unfortunately, even if we're lazy, we might have to do it, because soon, I think, for certain things, it already is a legal obligation to provide explanations. And these explanations should be robust explanations, not something that you change a pixel in an image and it changes the explanation completely. So this brings to the other point, you know, what I was mentioning of robustness is it's also a technical problem, not just that it would be nice to have predictions, but we also know that these architectures are vulnerable to peculiar behaviors that we humans are not vulnerable to. So for example, here we have an example. This is a school bus. Everyone agrees with it. It's even written there. And a neural network classified it accurately with high confidence that this was a school bus. But then someone designed an imperceptible perturbation. This is the perturbation that was added. I mean, this is a matrix, of course, and this is the matrix that was added to this matrix. And the transformed image still looks exactly like a school bus. I can't even spot the differences, to be honest. But the neural network now is confident that this is an ostrich. Now, when this was discovered, it was kind of big news. As far as I know, it hasn't really been solved as a problem. We understand much better how it arises. We know that if you were able to quantify uncertainty, actually it was shown here in Trieste, that if you were able to quantify uncertainty, so if you were Bayesian, you would not incur this problem, because the Bayesian model averaging would rule out these problems, but it's still an open problem. And it also affects any explanation. So there are methods to explain decisions post hoc. And they say, okay, this image, yeah, the network said it was a school bus because it's got a rear view mirror here. But then you change a pixel, nothing changes for the human, and the neural network will say, no, now it still thinks a school bus, but because it's seen this headlight here. We can't rely on that, you know. If we are diagnosing a cancer based on an image, and you change a pixel and says, no, it's not because of that, now it's because of that. That sounds very much like, you know, my Latin teacher when she was marking my assignments, and, you know, if I found that she had incorrectly marked something, she would suddenly find another mistake and confirm her mark. That not what we want of a good system. So it is a, it is a practical, social, legal problem. It is a technical problem. We have non-robust systems, but it's also an unacceptable ethical problem. So here is, an AI decided places where to monitor crime activity in Detroit. Yeah. So here is where they put the AI aided cameras, and here's where people live. They've put them all where people of color live, or Hispanics. I mean, even here there is this little thing. Oh, look, there is a little island of people of color, and they put the cameras. And similarly, here there's a little island of white people in the middle of black neighborhoods. They have not put the cameras there. So if we do that, and that is the massive risk, we're just amplifying biases and prejudices in society. Because what a neural network will do is essentially predict for the average individual with features similar to you. Now, if someone that wears glasses and has a little beard is a criminal, doesn't make me a criminal, okay? So we can't have decision-making mechanisms based on averages. That's just not acceptable. So I think these are really big problems that are technical problems and are huge hurdles in the adoption of AI or new data science methodologies in any domain. In science, because we want to have explanations by the kind of, the design of the whole enterprise. Science is about explanations, but also in applications. So something will need to be done to improve the state of affairs. And here it comes to what we're doing here in SISSA to improve the state of affairs. Well, we're setting up a lot of activity. So much of this activity was turbocharged by the award of the Dipartimento d'Eccellenza in Data Science grant from the ministry, which allowed the hiring of several faculty, including myself. And we're now starting a PhD course in theoretical and scientific data science, with the first intake coming in the fall. We are in advanced talks with other institutions in the region to set up an institute that could catalyze research on these topics. We're also part of a national infrastructure of the National Doctorate in AI, which again should start in October. And we have lots and lots of collaborations. More in detail, who are the people that are part of these, Dipartimento d'Eccellenza and PhD? Well, we're not very many, and we're all new arrivals. So Sebastian is our newest arrival. He just arrived in October from the École Normale Supérieure. And his research works really deals with how do neural networks learn? So what are the dynamics in the optimization, and how can we discover novel algorithms or prove things about the behavior of learning algorithms that may give us mathematical guarantees that certain degenerate behaviors like the ones that I've discussed will not arise, for example. So it's a little bit like finding paths in the mountains. And here's the mountain of the optimization landscape of a neural network. And here are two algorithms that have different behaviors. Alessandro Laio is kind of the padre nobile of the whole enterprise. He was the driving force to get the grant on the Dipartimento d'Eccellenza, and he's been around in SISSA for many years. And the kind of questions that he asks, I mean, he does lots of things in molecular dynamics and so on, but within this realm is mainly, how does the box work? So Sebastian was asking, how does it learn? Now, once it has learned, what does it mean having learned? And here is a cartoon from one of his most recent papers that shows how a trained network, so something that has learned, how the training meant that the points that at the beginning were all shuffled together become separated while you progress through the various layers of the deep neural network. And this sheds great insights about what really is going on in the box. Now, then here I am. I've been talking a little bit about generic things. One of the things I do work are exactly the adversarial attacks, but I also have been working a lot on biomedical applications. And here's a plot about the DNA methylation in the brain and how we can use it to distinguish different types of cells. I'm also a very recent arrival. In fact, on Monday, it will be 1 year that I'm at SISSA. And the fourth night of the apocalypse is Roberto Trotta, who joined us in April last year from Imperial College in London. And he is really interested in understanding how to model uncertainty, so the Bayesian side of machine learning, and how to apply that, particularly in cosmology, to theories of dark matter and the origins of the universe. And that's all I wanted to say. And thank you very much for listening to my rants for about half an hour. I don't know whether I was on time, but Luca was so polite that he didn't interrupt me. Thank you very much.
Perfectly on time, I would say, Guido. Fantastic, actually. So thank you, Guido. This was a particularly inspiring talk, so I really liked it. I really enjoyed it. And as you will see, there's a lot of connections. I mean, you already know, because one of the students that worked on the 6th edition actually worked with you. So
yeah,
there's a lot of interest in machine learning and artificial intelligence that is sparking inside master and high performance computing. And there's also a lot of interest that our students have sparked on companies working with artificial intelligence. And I think we will see some of these examples right after the next part of the event. So let me share again the screen, and let me go to this virtual ceremony for the diplomas of this year. So it's going to be a little bit complicated. So what I would like to ask is, if possible, to the students that actually read their names on the screen, if they can turn on the camera for a few seconds so that actually people can associate a name with a face. And this, I think, will be very, very interesting. So the first part of this discussion is going to be sort of boring, but I think each student deserves a few seconds in which at least we say what they have been doing during this last year. So this is what's going to happen. So this is the 6th edition of the Master in High Performance Computing, and we are currently working on the 7th edition. And in this March, we will open the subscriptions for the 8th edition. So what you're going to see today are the thesis works that have just been concluded. Actually, some of them have been discussed yesterday, and some of them have been discussed in December and some of them in February. And you will see some of these titles. So I will start with Matteo Alberti. So Matteo, if you can please turn on your camera if you're here. And his work has been sponsored by TechEdge, and it's distributed deep and reinforcement learning on cloud HPC systems. This was a very interesting thesis on arguments related to what Guido has been doing. And here it is, Matteo. You can actually grab your 5 seconds of of clapping hands from ourselves. So congratulations for achieving that.
Thank you already.
Yes. And then we have Sayed Aileh, porting the LBE3D to GPU using OpenACC. And this was, Sayed was one of the students that was sponsored by the ICTP, so the International Center for Theoretical Physics. And there we go. Please take a second to congratulate yourself for this achievement. I think these are all very nice and very important achievements. So thank you very much. Stefano Campanella is calibration of the geotop model using evolutionary algorithms from supercomputers. He's discussed the thesis yesterday, actually. So this was sponsored by HP3 which is an high-performance computing training research for earth sciences in collaboration with OGS. And the Thesis also was awarded a merit at the end. So every time you see this little star over here, is the committee decided that this was a particularly interesting thesis and got rewarded with an additional grade. And Miguel Castellano Merino, this is APIO, an asynchronous I/O pipeline for computational fluid dynamics code ASHI, and this was done in collaboration with HLRIS, so the High Performance Computing Center at Stuttgart. So if Miguel is present, I would ask him to turn on his camera. If not, I'll congratulate him anyway. So let's go forward. So Gianluca Coidesa, this is the OGSTM BFM I/O improvements. This was a thesis in collaboration with the OGS Center. And Gianluca, please take a few seconds to get congratulated.
Thank you.
You're welcome. And Irina Davidenkova, so the thesis is enhancing modularity of simulation software through modern C++ features on the example of Gadget, and this was discussed yesterday actually, and this was done in collaboration with INAF and SISSA. So thank you, Irina. Congratulations for this achievement. And Elena De Paoli, so implementation and performance studies of RMM-DIIS algorithm for Quantum Espresso, the GPU version. And this was done in collaboration with the Quantum Espresso Foundation and the Max Center, driving the exascale transitions, and the CNR-IOM, the Institute for Officina dei Materiali. And please, Elena, if you're here, turn on your camera and get your congratulations. And Farida Farsian, she was a PhD student sponsored by SISSA. It's novel application of neural networks in model recognition for cosmic microwave background data analysis. So Farida, if you're here, thank you very much for this approach. This was very interesting to see all these applications of the data science, new data science to novel cosmic analysis and cosmic data. Celia Loren, HPC implementations in the SciFem hydrodynamic model using the PETSI library and applications to modern architectures. It was an astonishing work done in collaboration with the OGS, with the Center for Geographic Institutes. So the thesis also got a merit in this particular case. And Celia, if you're present, congratulations. The Luis Gerardo Leon Vega, Nano Shy Tracker, an object tracking library for microbiology and an industrial cognition algorithm optimization. So this was done in collaboration with the CNR. Please, Leon, congratulations. I can see.
Thank you.
You're welcome. Antonio Sciarappa, numerical methods for road tunnel safety assessment. And this was done in collaboration with Lombardi. And it was a very nice application of artificial intelligence to safety assessments for tunnels and roads, and to understand how our Italian roads are getting analyzed by machine learning and artificial intelligence very recently. So this was also very interesting. Antonio, if you're present, congratulations to you. And Martina Teruzzi, so this was a collaboration with the CEPENA, which is the Center for Research of the Fincantieri Group, actually. So this is parallel implementation for complex graph analysis with application in modern passages ship safety management. And it helps in understanding when a ship can actually return safely to port, where something is irremediably broken in this thing. So it's very important research in terms of how to assess these type of measures. And I think Martina did a very good job in this direction. So congratulations to Martina.
Thank you.
And Christian Jasurog, he's been financed by the ICTP, so sponsored by the ICTP, and this is modeling and linear chip sequence data using statistical analysis and MMDiff2, and this is also in collaboration with Professor Guido Sanguinetti, who was actually the supervisor of this work, and sponsored by the International Center for Theoretical Physics. And Jez, if you're present, congratulations. The Nesrin USP is detection of recurring behavior in banking data. Again, collaboration with the ICTP, so International Center for Theoretical Physics, and Prometheia. So congratulations, Nesrin, and she also defended yesterday.
Thank you.
And finally, last but not least, Alberto Cazzaniga, and his thesis is the representation learning and hierarchical clustering for microscopy images. And it's been done in collaboration with CNRIOM, and he's been awarded for the best thesis of 2019-2020. And it is actually my pleasure to let him take the ground for the next few minutes, not too much, but just to give us an idea of the best thesis award for this year. So congratulations, Alberto, and the screen is actually yours. So please go ahead.
Okay, try to share my screen with a second at a time.
Yes, that's perfect.
Perfect. So good afternoon, everyone. And first of all, I want to thank Luca and all the organizers of this event for giving me the opportunity to speak, and particularly for providing me with the challenge of talking about something related to AI after the thought-provoking and wonderful talk from Professor Sanguinetti. But going down to the topic, today I want to discuss progress in my thesis with title Representation Learning and Hierarchical Clustering for Microscopy Images, which has been conducted under the supervision of Stefano Cozzini and Alessio Ansuini, and in collaboration not only, as Luca said, with the CNRIOM, but also more recently with other science park. And also I would like to acknowledge the support in terms of infrastructure from both Exact Lab and again with the cluster C2 HPC, and again from RS Science Park with the newly created cluster Orfeo. The project, the project I'm going to discuss today can be framed in the context of the NFFA Europe project, which is a European initiative aimed at connecting several laboratory facility and research institutes around Europe working on problems at the nanoscale, mainly with the two objectives. The first is to move the art and carpentry of the various from the single laboratory to the art and craftsmanship of the statistical interpretation of the data coming from various sources. And the other one is to organize essentially the data flow, the large amount of data flowing from the various laboratories, meeting the core ideas of the FAIR principles, which are findability, accessibility, interoperability, and reusability of the data. But in particular, my project focused on the case study of SEM images, which are images taken by means of a scanning electron microscopy technique, which can be summarized as passing a beam of electron over the surface of a nanomaterial, typically at the scale of the nanometer or the micrometer, in order to detect the details of the material itself. And the objective essentially is to analyze a fairly large data set collected in the last few years, both at CNRIOM and at various other facilities, in essentially in a hierarchical structure that somehow contains information about the content of each and every other image. In particular, one can think about the hierarchical structure simply as a folder, subfolder subdivision with the additional datum that the distance between two folders somehow, with the additional datum of a distance between two folders that somehow should explain how far in content the images contained in the folder are. And we try to develop techniques that are general enough, hopefully, to be applied also in another type of microscopy images. And we try to, as much as possible, to make them such that future data availability can make the other images integrated in this data set. As in many other projects in data science, perhaps the main character of the work is the data itself, and we're giving at end three different data sets. The first is the full SEM data set, which is a data set of 150,000 images collected by various microscopes, all of them carrying a unique identifier, and all of them of the same size, 124 by 768 pixels. And also several metadata on the images, both scientific and more technical, is available, such as, for instance, the scale at which the image has been taken. And this has been collected thanks to the work of previous other MHPC theses, for instance. The second dataset has been humanly crafted, and a subset of 20,000 images have been manually labeled in 10 categories that we denote as NFFA categories, as you can see in the central part of the slide. And it's immediate to observe from distribution plot that the classes are very uneven, in fact. And more specifically, especially the large populated classes are quite variable in terms of thematic content. For this reason, in a further dataset, much smaller but extremely well curated, has been humanly labeled in 36 classes, this time organized in a hierarchical fashion, as you can see here, and essentially with the objective of further refining the first classification that was not entirely satisfactory for the scientists working on this type of experiments. And in a sense, the objective of this work is to attempt to perform an automatic subdivision very similar to the one of the hierarchical subdivision that we see here, but on a larger amount of images. The strategy that we employed is made essentially of two parts. The first part is to try and extract representations from the initial datum of our dataset that is lying in a very high dimensional vector space by means of a convolutional neural network, trying to achieve essentially two main results. The first is to somehow compress the information. I mean, we're going down some order of magnitudes, couple of order of magnitudes from the initial dimension. And at the same time, we want to try to find representations that was such that the relative distances between the transformed images is going to be, in a sense, contain information about their distance in content. And afterwards, we try to cluster these data, I mean, these representations in a hierarchical fashion to obtain the desired partition. In order to do so, of course, many questions need to be answered. First of all, which kind of model are we going to use? How are we going to train the model to actually produce meaningful representations? And afterwards, also the problem of clustering and dimension is quite non-trivial, as we're going to see. The first thing to do is to select a model, and in order to do so, we do a very rough approximation of our pipeline, and we compare several modern architecture that has been employed for computer vision. And as you can see from the result, we end up selecting a ResNet 50 architecture. Essentially, this experiment has been performed more or less in this way. We take a pre-trained network on the ImageNet dataset. Our images are, yes, very different from the images in that dataset, but not that different, so that somehow performing a forward pass is still meaningful. Afterwards, we reduce the dimension and we by PCA, and then we compute k-means clustering just to have a proxy of how much the result that we obtain is aligned with the 10 categories that we know, in fact, having a meaning in terms of content. Again, we selected in general architectures in the ResNet family seems well performing in this kind of task, and for this reason we select this model. Not gonna spend much time in describing in detail what a ResNet 50 architecture is. I'm just gonna say that it's mostly made of convolutional layers, and the fact that such a deep network can be trained is essentially given by the presence of residual units that allow effective training even in presence of depth. The second question is how we're going to train this model in order to produce meaningful features. And the first approach is classical. Somehow we look only at the label part of our dataset, and we train this model, we learn the weight of the model, trying to essentially, by stochastic gradient descent, trying to make the model predict as well as possible the label assigned to each image in the label part of our dataset. Once we reach let's say, satisfactory accuracy, or once we stabilize, essentially, we stop, we freeze the weights, we do a forward pass, and we obtain the first type of representations we're going to consider. In order to have a qualitative, let's say, analysis of the representations, we do two things. The first, we compare essentially the only on the label part of the data set, the distance, how much the distances of between the images respect essentially class membership. So we compare the distance matrix on the label part of the data set with the discrete distance that is just defining class membership. And as we can see, we see that some of the features necessary for classifying the images have been, of course, understood in the last layer before classification. The second thing we do, and it is going to be quite relevant for the clustering procedure, we measure the intrinsic dimension of the extracted representations using the 2 nearest neighbor algorithm developed by Lai, Rodriguez, and other collaborators, because we want to, in fact, verify that what has been recently observed in several circumstances, as has been observed in several circumstances recently, or several data sets, and as in fact Professor Sanguinetti was showing in some of the previous slides, in fact the data in the last layers of a neural network, in the case when we're analyzing data sets of images, tend not to fill the whole space, but just to lie on a submanifold of substantially smaller dimension, even if it's embedded in a very high dimensional vector space. The second type of training goes under the umbrella of supervised methods, and is based on a relatively classical idea, which is the one of the triplet loss, let's say goes under the name of the triplet loss function, and consists essentially in doing the following. Once one has a labeled data set, and suppose for the moment that it's already embedded with good features in a fixed vector space, the triplet loss function was introduced to try to learn a linear transformation of this vector space that would ensure as much as possible class separability by a certain threshold. In particular, one to do this considers triplets of images, where images with 2 images that are in the same class and 1 image that is in a different class, and try essentially to push far aside images in different classes and pull close together images in the same class. Essentially, we kind of, in a more modern approach, tries to mimic this idea by combining it with a head that is given by a resonant 50 model in this case, to try to learn this time a nonlinear embedding that somehow has the desired property of separability. And again, here we monitor the distance matrix between the distance matrix of the extracted representations. And as you can see, what is interesting to notice is that of course, these are well aligned since we're doing, training on a labeled dataset, well aligned with the class subdivision. But in particular, it's worth noticing that while in the minority classes that are extremely, let's say, well defined in terms of content, the distances are very small, there is still some non-trivial structure that emerges from the majority classes. It measures also in this case the intrinsic dimension, and it's comparable to the values we showed before. The last technique that we experiment is a little bit, in fact, more experimental, and essentially goes along the ideas of the deep clustering algorithm. Essentially, what was does is the following. We consider our resonant 50 model without any classification head. We do a forward pass. We consider the representations at the layer before classification, and then try to perform essentially a rough clustering here. This clustering assigns to each and every other image a pseudo label, which is just given by the class membership, and we train for 1 epoch to try to recognize this pseudo label. As the authors of the original paper show in several data sets, and as we can also partially observe, one can leverage on the low signal that is given by essentially the fact that we are using a very expressive convolutional architecture, initial signal. During the training, we can leverage on this signal in order to produce meaningful features. And even here, despite, as shown by the distance matrix of the extracted representation, since we didn't input any datum concerning the classes, but we still see that minority classes are essentially well identified despite the absence of labeling. We measure also the intrinsic dimension. In this case, it's slightly smaller, around 7, and it's not yet clear if this is given by a good compression of information or rather by the fact that some of the relevant features have not been detected. So to summarize, this stage, after one of the 3 procedures before, we are left with a data cloud in a relatively high dimensional vector space, 2048, of points where distances essentially should describe image similarity. Perform a hierarchical cluster in this setting is non-trivial, and we do not have any a priori knowledge of the shape of the clusters. And for this reason, we decide to employ a density-based type of algorithm, which essentially is founded on the core idea of the density peak algorithm developed by Rodriguez and Layo, which can be roughly summarized as follows. One is a data cloud, and essentially must be able to estimate the local densities of the various data points. The assumption is that the centers of the clusters are the peaks, local peaks of the density function, and center clusters should not lie close together, close to each other. So essentially, one can plot the density for each data point, can plot the density function against the distance from the closest point of higher density, and the outliers of this plot are in fact the center clusters. Afterwards, all the points are assigned to the corresponding cluster just by giving them the same label as the one given to the closest point of higher density. The problem is in employing straight ahead this algorithm in our setting is first of all that a local estimation in such a high of the density in such a high dimensional vector space is a priori not feasible. Secondly, it's not trivial in general to detect which are the outlier and hence the number of clusters. But recent development also done by Alex Rodriguez, Layo, Maria Rico, and Elena Facco somehow outputs an advanced version of this algorithm that, first of all, in the case when the data cloud, as in our case, lies on a submanifold of much smaller dimension, enables us to obtain a reliable estimate of the local density. Secondly, an automatic selection of the peaks of density, of the relevant peaks of density, is done by means of a statistical parameter that controls how much confident we want to be on the fact that the cluster is separated from another. And furthermore, this algorithm not only describes the peaks of the density function, but also the saddles between different peaks. And for this reason can be generalized to obtain, in fact, not only a partition of the dataset, but a hierarchical partition of the dataset, as we're interested in. We perform the algorithm on the structured representation, and the outputs are summarized in this slide. And I want to make 2 main observations here. The first is, of course, how do we evaluate? It's not trivial, of course, to evaluate if the algorithm was successful or not on points where we do not have label. And for that, the only thing that we did and that we continue to do is to essentially confirm the good result of a clustering with the scientist CNR-YOM. But as a proxy, here I show just on the label part of the dataset how much the clusters that we obtain somehow automatically are aligned to the previous classification in 10 categories. As we can observe, when we consider only the label part of the dataset or the full dataset, we have a good alignment of the clusters with the 10 categories, especially in the context of the supervised methods, but still showing that essentially what we obtain is a refinement of the previous human effort of classification. And also we can observe that there's a non-trivial alignment also in the case of unsupervised techniques, despite the fact of not having introduced any information about the labels. Thanks to the study of the peaks and the saddles given by the algorithm, we can then not only study, in fact, alignment with the previously defined classes of the various clusters that you can see here on the left, but also the hierarchical structure of the various peaks of density, and how somehow have a sort of visual representation of how they are organized, projecting in a certain way into dimensions. I want to also show some of the outputs of the clustering procedure, and somehow stress at least two things that for us were a little bit surprising when observing the results. The first is the following. It turns out that images, even images that are at different scale, whenever they have a very much compatible content, as you can see in the case of triangular pillar and porous sponge, then these objects are put in the same class. Differently, in the case when the scale is relevant for determining the content of the image, the images are separated in different clusters. But still, what is quite interesting is that in the hierarchical, by studying the hierarchical distribution of the various peaks, we can see that the zoom in for instance, of waveguides is very, very much close in the hierarchical dendrogram to the cluster instead of much larger waveguides. I'm going to conclude here just with a couple of other images. The first in the middle is a couple of results from that have been obtained in collaboration with Tommaso Dodani on employing very, very much similar techniques on now another different type of microscopy images. This data set is a little bit, of course, is very different from the other one and presents different challenges, but still, at least we can say that some of the techniques can be transferred, and hopefully Tommaso will report to you soon some more progress in this direction. And then in the semicircle that you see, there are many known faces of previous MHPC students that most of you know, and that somehow have played a very important role for all the history of semi-images, and without whom this project would have not been possible. And I stop here and thank you for the attention.
Thank you very much, Alberto. So one thing that I didn't mention is that at the end of the 3 talks that we have today, we will give a few minutes of questions and answers for all the speakers. So both Guido, Alberto, and Peter will have the occasions to answer to some of the questions if the audience has some of those questions. So this part will be recorded right after the 3 talks, just for logistic and regia sort of reasons, right? So it is now my pleasure to introduce to you the success story of the past. So Peter Labus, his journey from MHPC to his current position at the Fraunhofer Institute of Industrial Mathematics. And he's been one of our best students in the past. And I think his thesis was something like about quantum chromodynamics or something like that. I don't remember exactly the title, but I think this was pretty much it. So Peter, I would welcome you on board, and please tell us your story, how it went after MHPC and what you've learned and what has happened so far. So the screen is yours, you can choose.
Super, thank you very much, Luca. Much appreciated. In fact, let me start this. In fact, I'm incredibly flattered and honored to present my story here as a success story. It's a story from going from physics, theoretical physics, to HPC, and from there to AI and deep learning in particular. Actually, scalable deep learning. So HPC is still a component there. And it's a story that at the moment resides at the Fraunhofer Institute for Industrial Mathematics in Kaiserslautern, Germany. That's my home institute here, a photo that you see on the screen. And for all the graduates and current MHPC students, if this appears to be a coherent story or a story that is sort of linear, then don't be fooled, because that only appears as such in retrospective. And if your story doesn't appear coherent yet, don't worry, because things will emerge, and that's actually what happened to me. Okay, so for everyone who doesn't know me, I'm Peter. I'm a German native. I studied physics, figured out quite quickly that I'm not made for the lab, and so I switched to theory, and then did a master's in theoretical physics in Munich. And after that, I decided, yeah, I want to continue doing some research, but I want to go abroad. I want to go to some other country, learn another language, and maybe escape the bad German weather as well. So I decided to move to Italy, and namely to Trieste, to join SISSA for their high energy physics PhD program. And I ended up screwing around with quantum gravity with my dear supervisor, Roberto Procacci, trying to build a theory of everything. Well, big words, but what I actually did on a day-to-day basis was solving integrals with pen and paper mostly, and then trying to use computer algebra systems like Mathematica to do symbolic manipulations. And about a year or so into my research, I heard about and learned about the new master program for high performance computing, organized by SISSA and the ICTP. And I was just thinking, I always wanted to learn some decent programming, and it was something new and it looked exciting. And I was also thinking, okay, maybe I could use some numerics for my actual PhD research. So I applied, and fortunately enough, I got into the program. So that was back in 2015, being the second edition only of the MHPC. And with this very nice people and friends listed here, I wasn't able to find a nice group photo, unfortunately. We survived a year of quite intense lectures and classroom sessions. And after that year, I was eager to make my hands dirty and get actually into some HPC projects and do some reprogramming. And as my dear friend Marlon Brandes would say, show me the money. That's what I wanted to say, the money. Actually, in fact, I didn't see the money for another couple of years or so, but I've seen and met some interesting people and done some interesting projects, two of which are listed here. So in particular, I partake in the Praise Summer of HPC in 2016, where I had the opportunity to go to the Jülich Supercomputing Center and work on some Markov Monte Carlo, Markov chain Monte Carlo code, where I implemented some Krylov solvers and did some CPU optimizations. And okay, that led some speed up on the code and some improvement in memory print up. But what was the cool thing is that we could actually do new physics, and wrote a paper about that. But in hindsight, I must say what I really learned there is that you should expand and build some range, that you should actually be looking into things you haven't done before, new topics, and then they might lie outside of your specialization. They might lie outside of your field or subject, but they might even lie outside of science. So I think exploration as a computer science term is very important. And the next thing is building a network of interesting, talented, and reliable people. And this is also something I'm very grateful for this project, that I met people like Stefan Krieg and Thomas Liu, who I'm still doing research with, and actually we're looking into co-supervising a PhD student in the near future. Another topic, Lucas said it already, was my master's thesis project, where I was building new stencil operators for lattice QCD codes, which had the target architecture CM5, that doesn't even exist anymore. And that was actually fairly difficult, but not for the reasons you might think, that we wanted to optimize the hell out of these kernel codes. It was difficult because it was the first huge code base I had to handle. Huge, I mean, in terms of, I don't know, 10,000 lines of code or 20. But it was the biggest thing I've ever seen. It was really hard to navigate through that. It actually took me weeks and maybe months to understand how that all worked and where I had to change things to implement new kernels. And so what I learned there is that you need to stick to a problem as well. So yes, look around, but also stick to the things that you do until you succeed. So that's the exploitation part, yeah, of your computer science lingo. And another thing I started to do there is spend continuously some time in educating myself. So some 10 or 15% I spend on a daily basis to learn about new things. And that's what I started there. And in particular, I discovered MOOCs, so this massive open online courses that are offered from great universities all over the world. And I studied there, I started to study machine learning and deep learning in particular. And actually, I grew interested in that much that after returning to Trieste and finishing my PhD, I decided I wanted to work in this area. I wanted to work in deep learning. But that turned out to be somewhat difficult because obviously I couldn't show for any expertise. I haven't done a PhD in machine learning. I didn't have any job experience with that stuff. So I was looking around and came across a job advertisement that read pretty much as you see on the left-hand side by a company called Fraunhofer. This is a German company, the guys who invented the MP3 format. And they were looking for some research scientists in large-scale machine learning. Actually, I read, you always wanted to train a CNN on 100 GPUs. We're working on it. And I was saying to myself, yes, please, that's exactly what I wanted to do, and applied. And in fact, I got hired in the end, but not because I knew about physics or what I knew, the little I knew about deep learning or machine learning by that day, but actually because of the knowledge I had about HPC and parallel programming. So I joined the team. You're seeing that on the upper right, it's a department of about 50 people. As a research scientist in January 2018. And at Fraunhofer, we are in between academia, pure academia, and the private industry. And in particular, we're spending about 50% of our time doing basic and applied research, and the other half doing industrial consulting. And after a year and a half, I got a promotion being the team lead, now overseeing all our activities in scalable machine learning and deep learning. And there's a lot of interesting topics I would like to talk about, but due to the lack of time, I will actually today focus on the project I have been originally hired for, and I'm still managing up to this date. And that is building a distributed framework for deep learning and training deep neural networks in particular. And this is where I finally actually saw the money. Now, what does HPC have to do with deep learning, or does deep learning have to do with HPC? So deep learning is the stuff about deep neural networks, or neural networks, artificial neural networks, that started about 12 years ago, when there was enough compute capability to do interesting stuff. And in this about, 9-10 years, since then, we have seen a lot of progress, in particular in computer vision, in natural language processing, and in reinforcement learning. These are probably the three categories that had the most impact in terms of products and services in the industry, but there are clearly other fields as well. To give you some examples, if you don't know them already, in computer vision, we're now not only able to classify, dogs and cats, but we're actually able to generate high resolution images from scratch. Yeah. So particularly the photos of these two people, these are people that don't really exist. That is the state of the art done by StyleGAN from the year 2020. In the same vein, we now have large enough language models like GPT-3 from OpenAI that are able to generate texts, for instance, news articles that aren't or almost aren't distinguishable from humanly written news articles. And we have successes in reinforcement learning. For instance, the whole line of research done by Google DeepMind, including AlphaGo 0, AlphaZero, AlphaFold, that is used for drug discovery right now, but also, for instance, research done at OpenAI and Microsoft. As an example, I brought here the OpenAI Stota 2 engine. Now, a lot of that has been enabled through algorithmic development, clearly, but another very important factor has been the increasing amount that people were willing, the increasing amount of compute power that people were willing to put into AI, machine learning, deep learning training. And in particular, since 2012, as OpenAI themselves researched, there has been not a linear, but actually an exponentially growth in the amount of compute power that people are willing to invest into AI. And even more incredible is that the doubling period amounts of only approximately 3.5 months, which is much outpacing Moore's law original growth rate of about 2 years. Okay, so if you want to do AI today, or if you want to be able to do AI in the future, you will need to do HPC. This is how AI and HPC are connected. Now, 3 years back or so, when I started to talk with people about distributing deep neural network training and such, a lot of people said, yeah, well, that is just matrix-matrix multiplication or matrix-vector multiplication. And that's, of course, true for fully connected layers and even for convolutions, because you can rewrite them. And that's even true for transformer architectures today. So they said, yeah, well, that's what we figured out in the 80s already. So that's trivial. Let me show you why this is actually, in fact, not as trivial as you might think. The reason there is that deep neural network training is inherently sequential and iterative. So if you've never seen a DNN, a deep neural network before, here's one resonant 50. Alberto just showed us the exact same network as well. You see this nice skip connection on top of it. And here you see what most DNNs usually are, mostly linear chains of sequentially dependent operators. And these operators, convolutions, fully connected layers, etc., are, as I said, usually called layers. But since they are sequential, the output of one layer needs to be fed as input to the next layer, and that means these two layers can't be executed in parallel. Okay, so there's a sequential dependency. Things get even worse because if you traverse your neural network from the left to the right, which is called the forward path, we've heard all about that, you need to traverse it from the right to the left again in the so-called backward path. And this backward path has to be strictly performed after the forward path. Okay, and then you do this backward path to update your trainable parameters, your learnable parameters, your weights, and this weight optimization is actually this optimization procedure Guido told us already about. It is actually an iterative algorithm itself. So all this training is inherently sequential and iterative, and you can't get away but not having repeated synchronization points. Now, Amdahl's law obviously tells us If we have the synchronization, if this turns to sequential execution, we are doomed. We can't scale. Okay. So what we need to do is hide communication necessary for synchronization as much as possible behind useful computation. And to do that, we need many layers of parallelism, and we need a good communication API or library. Now, as a short overview, you might know that already. What are the three parallelization, or what are at least three parallelization strategies to distribute a deep neural network training? We have data parallelism, we have pipelining, and we have layered parallelism, the latter two of which are also called model parallelism from a standpoint of deep learning practitioners. An HPC person would call it task parallelism. And what do they do? So in data parallelism, I take my mini batch or batch that I feed in one iteration to my deep neural network and split it into micro batches. Now execute these micro batches on different workers or processes or nodes. And that's actually easy to implement, or fairly easy to implement, and gives you a lot of potential for strong scalability. The problem with that is only it doesn't allow you to train deep neural networks of any size, and that's a problem because deep neural networks get larger and larger by the day. Why is that? Yeah, because you have to copy your deep neural network with all its weights and activations to all of your processes, to all of your workers. To get around that, you need model parallelism, and that is done, for instance, pipelining, where you split your deep neural network at layer boundaries into partitions, and that now allows you to train DNNs of any size. But it's hard to achieve a split that gives you good load balancing, okay? And it's also more difficult to implement. So the problem with the load balancing, you can actually circumvent with the use of layer parallelism, where you split individual layers or operators into partitions, which is always necessary if you have very large layers. And this can improve load balancing then. The problem here is only that it's hard and time consuming, because you have to redo this for every single operator, so every single layer type in your deep neural network. And it also has the most complicated communication patterns, which use domain decomposition and ghost cells and the like. Now, back in 2018, there was no framework that deep learning framework that was implementing all these three strategies. And as far as we know, there's still none that implements all of that under a common interface without forcing the user, who might not be an HPC expert, to specify and help the software get these distribution strategies right. And so we decided to build our own distributed deep learning framework called Tarantella to provide such an interface. And we decided to build this upon TensorFlow, which is a well-spread and well-used deep learning framework developed in open source. So Tarantella has a number of key points or aims. In particular, we wanted to overlap communication with useful computation as much as possible. We wanted to fully support the synchronous optimization scheme of SGD, ADAM, and so on. Why is that? Because we wanted to be able to reproduce result that one obtains on a single GPU and single node execution. And we wanted to fully support the interface given by TensorFlow, TensorFlow 2 actually, and Keras, and don't put any additional burden on the user. Now here's a short sketch of how we implement data parallelism and model parallelism in Tarantella. On the right-hand side, for data parallelism, we take the compute graph generated by TensorFlow, that's the green bubbles on the left-hand side, and replicate it on every node on each worker, extending it with all reduce operations that are not implemented in MPI, which you might think, but in our own communication library that is based on the GASP standard. And what it does is we can execute these all reduce operations asynchronously and non-blockingly. And that means we can start sending data for each layer that carries weights as soon as we have the partial gradient updates for these weights, and then continue at the same time with our backward propagation doing useful work, and only require the all reduce to finish where we might, but may also not, wait at the latest point we can, that is when the back propagation is finished. And in this way, we overlap communication with useful computation done in the back propagation. Model parallelism we implement with, well, I'll show you the pipelining scheme here, where we get overlapping communication by having a non-blocking send-receive sort of pair, also using the GASP communication standard, where the send starts to send data over the network, but then quickly returns so that other useful computation can be carried out. All right, and to wrap things up, everyone always wants to see benchmarks. So I brought some benchmarks here. This is actually Tarantella showing strong scalability for ResNet 50 training on CPUs and GPUs on the ImageNet dataset. On the left-hand side, this is a SuperMUC at the LIZ in Munich, which is an Intel Skylake machine having an omnipath network. And there we compare ourselves to the state-of-the-art framework for data parallelism called Horovod that was developed at Uber. And we see that we strongly scale quite well until about 250 GASP ranks. And we do actually at least as good as Horovod and sometimes better for small node counts. And this is actually preliminary results. So this is stuff out of the box without having anything fine-tuned. So there's still tuning potential we still want to uncover in the future. On the right-hand side, you see a GPU machine, which is an IBM Power 9 system with NVIDIA Volta V100 GPUs, 6 of them per node. And also there, we see good, strong scalability. And also there, we are at least as good as Horovod. All right, and with these, I want to give you some pointers. So if you're interested in any of what I said, go over to tarantella.org. There you find the links to our GitHub repository. So Tarantella is actually open source. You can download it. You can learn more about it on our Read the Docs documentation. And we're always looking for smart people. So if you're looking for an internship, for a master's thesis, or for a job, or you want to collaborate with us, yeah, please get in touch. You can send me a request on LinkedIn. I will definitely connect with you. You can also send me an email, or just head over to itwm.fraunhofer.de/ml to learn more about our current and future projects. With this, I would like to thank you, and I would be very happy to take any questions.
So congratulations, Peter, and thank you very much. This has been a very inspiring talk. So I would like to have Stefano give us a final remark before he has to go, because I know he has an appointment at 5. And then after that, I'll collect all the questions from the audience for all our speakers, and I'll be very happy to moderate the discussions afterwards. Please, Stefano.
So very briefly, congratulations for the excellent talks today, and for the globally about the event. I have learned many things that, and I'm sure that the activity of the master will continue even after my direction, because I will finish in October. So this will be my last graduation ceremony. So so good luck for I see many prospects of evolution of this activity. So I'm very happy that I've hosted it in these years. In fact, the academic year of Peter Labus was my first at SISSA, so 15-16. So we are perfect synchrony with with your talk.
Very good. Okay, so if we have any questions from the audience for any of the speakers of today, so for Guido, for Peter, or for Roberto, please raise your hands or write your questions in the chat, and we'll send it to everyone. Or curiosities or personal questions about career or inquiries about a job or something like that. So don't be shy. I mean, I know there's a lot of MHPC students who are just freshly graduated. So if you want to ask about how it's going, and oh, there's a question for Peter right away. So actually, do you want to read it out, Peter, directly, or shall I read it to you?
Sure, can do that. So how do TPUs affect the landscape of prioritization in deep learning, machine learning? TPUs in particular, I don't know. There's a lot of new novel hardware around, and a lot of startups try new things, which obviously makes it hard to adjust hardware and software at the same time. Okay, so I think this is so I see a challenge, so an opportunity and a challenge. The challenge is how do you develop new novel hardware that will also support new forms of algorithms in the future and make them possible. And that's why I think a lot of companies actually shy away from this novel hardware and stick to the not quite as novel anymore GPUs. Okay, and the opportunity obviously is that you might be just way more efficient. And in particular, if it comes to things like embedded devices and IoT, you know, novel hardware and novel designs, such as TPUs, is just a thing you might need. Hopefully that answers your question. Thank you.
Thank you very much, Peter. Any more questions for Guido, Alberto, or Peter? So actually, I do have a question, which is a personal question, Peter. So did you ever think for a moment that you were doing the wrong thing during MHPC? Because I've seen many students having a difficult time at the beginning in the first few months, and then thinking, oh, this is not going to work for me, or this is not good, or things like that. And then after that, you know, looking in retrospect, what can you say to those guys? And is it true that this happens? And what do you think about it?
Definitely. I mean, I didn't say this explicitly, but I think doing this master's was probably one of the best decisions I've made in my life. And actually, I remember Roberto saying to me, my PhD supervisor, finally, yes, let's do that, because it's something you can use in life. And yeah, it has been difficult for sure. And for instance, when starting my thesis, I was struggling a lot. But I think you need to persist, and then once you get the degree and you like what you're doing. So I really liked programming. I really like parallel programming, and I enjoy it to this day. If this is the case, then there will be opportunities for you, and there will things will work out in terms of companies and networks and jobs, I think.
Thank you very much, Peter. I might ask the same question to Alberto. So did you ever have a time in which you thought, well, this is not the right way?
No, I mean, the master has been great as usual this year, with the only difficulty that after February it has been done online, and I think it's a little bit tricky, of course, because one of the best part, I think, of the master is to be closed in the same room with 10 other girls and guys all quite motivated to learn. That most of them know already quite a lot of things, but also want to learn something more. And the fact of being far away, far apart, is not always easy. So it's going to be a challenge for the next students of the next year and of this year. But I'm sure I mean, at least in our case, for sure, the organization did the best to overcome even the hardest difficulties. But I hope for the master that he will be back in the room very soon.
Yes. I do have one question for Guido as well. So, Guido, if you were to talk to a newcomer, I mean, machine learning and deep learning is an ocean of knowledge that seems to be out there. And if you go online and search for deep learning courses, you get something like thousands of new courses and thousands of lectures that you can actually follow. And maybe not all of them are useful, but it looks like it's an humongous amount of data, as we were saying, that you have to navigate through. So if in your own experience, what's the best way to approach these type of things for new students, for newcomers, for people interested in trying it out or figuring out how this works?
Well, it's a very good question. I suppose, you know, it depends what you want to do, but, you know, it seems to me that the younger generation learns in a different way from the way I was learning. Yeah? So I kind of always wanted to try to understand, you know, linear algebra and then functional analysis and then maybe deep neural networks. But you do have this infrastructure of software that you can use relatively easily. So you can be a practitioner of, you know, if you want to get a job in a software company doing deep learning, maybe you don't need to be a mathematician. But if you want to understand a bit what is going on, I think, you know, I would start from the linear algebra and Bayes theorem and you know, regression and stuff like that. Because at the end, you know, it's doing it there's a huge problem of lots of fancy terms that are poorly defined, or actually don't mean anything in many cases, or mean something totally trivial that, you know, if you told me what it was, I would have understood a year earlier. But, you know, that's a real problem. I think, you know, some sort of pruning of the
hype.
Little misleading bits would really help, and understanding at the core what is going on would help.
Also, if you have questions for the audience, like Guido, Peter, and Berto, to the students, please feel free. I mean, this is an open roundtable discussion. So.
Well, I have question remark to Guido as well. I mean, in fact, what you've been talking about, adversarial attacks and explainability in particular, is a huge topic. And in fact, a lot of industrial clients shy away from deep learning and such, because we cannot guarantee that. So I would be curious in what sort of approaches in terms of, say, explainability you follow, or what do you think is the most promising ways?
So, okay, so I didn't really want to advertise too much, but one thing that we've done very recently, we had a NeurIPS paper last year with some collaborators in Oxford and here at UNTS. We showed that, I mean, theoretically, we proved that some of these issues with adversarial attacks exist precisely because the data really lies on a very thin manifold in a high dimensional space. And what happens is that, of course, you know, the loss becomes constant on the manifold in the infinite data limit, but in any direction that goes off the manifold, there is no constraint coming from the data. So the network can take whatever value it wants, and that is what gives these very, well, that's how we understand the minimal changes. I mean, you have, say, you're in 1 million dimensions, you have data that lies in 20 dimensions. We've seen these intrinsic dimensions of 15 or something like that. That means you essentially have 1 million directions you can go off. Chances that the gradient is very large in one of these directions is 1, essentially. Yeah? And what we've shown is that precisely because there is no information in the data about what to do outside, if you have a Bayesian ensemble of predictors, then you will have some that do one thing, and some that do the opposite, and some that do one thing in another direction. So if you do Bayesian model averaging, you can remove this problem. Now, obviously, the problem is doing Bayesian computations for ResNet is really not trivial, and I'm not one person that believes that Monte Carlo dropout is actually a Bayesian computation. But that also seems to hold, so we've just posted a preprint for interpretability. So I think what we need to do, at least, so if you do these post hoc checks of what are the most important pixels,
yes.
Yeah, you change one pixel and then suddenly every explanation changes. But if you are Bayesian, you get stable explanations. And so, post hoc explanations may be okay, but they need to be stable. So I think we need, one promising direction is to look at ensembles of predictors which are randomized in a way that stochastic things that emerge because whatever reason your optimization is really unconstrained in many directions get averaged out. So that's, I think it's a promising direction. It doesn't explain why at a deep level. It doesn't give us a model of the world, which is what we would like. So I think in that respect, from the point of view of a scientist, actually, I think deep learning is fundamentally flawed because it moves away from understanding. It moves purely to prediction. But there's a room for prediction. Companies want predictions, and that's totally fine.
True.
But at some stage, we need to think about abstraction and models and understanding at a more fundamental level than just giving predictions.
Sorry, Guido. Would you agree that very often you need external info in order to understand where to go?
Yeah, so that's totally true. So for example, not every prediction is the same. Not every application is the same. Yeah. So 15 years ago, I mean, even less than 15 years ago. So I went to a workshop of kind of all ERC grant holders in machine learning about 2014 it was. And there were a bunch of computer vision people. And at that stage, most computer vision people still did not really want deep learning. And they had spent most of their time trying to build models that gave good priors of images. And when they mean good priors, they must include edges and things like that. It probably is not a very clever idea to spend a lot of time thinking about what is a good prior generating mechanism for images. I mean, there's no fundamental reason why the wall behind you has got tiles which are dark and white and so on. So in that respect, A, you have no good reason to come up with a model, and B, you really have tons of data. So just learn the marginal distribution of the observables and sample faces. It is a lookup table. Yeah. So yeah, those faces that Peter showed us do not exist. But come on, they are very close to faces that do exist. Now there are issues, of course, in generating generating human-like text could be ethically problematic. Or there's also huge problems. You use neural machine translation on diplomatic documents, and you get it wrong, but it still sounds exactly like it's a human. What do you cause a war or something like that? Because they believe that they said that. While 10 years ago, you would read something that was translated by a machine, and you would say, "Yeah, right. This is obviously not anything that was said by a human." But what I mean, images certainly being fully data-driven, I don't see a big problem. Unless they're images, say, of proteins, in which you may want to have some strong background info. That's the whole point. So, to build a model, you need something. So to build a model that is competitive in terms of prediction, you need something that enables you to have good priors. And then you have to combine it also with nonlinear observation models. And that's the crux, you know, being Bayesian with models that have science inbuilt and also nonlinearity. That's difficult.
Any more questions or curiosities? Well, if not, then I would like to thank again. Oh, Peter from Federico Society. Do you think compilers will ever be able to play a role in automatic parallelizing deep learning?
That's a good question. In that sense, what is a compiler? Okay. I don't know. I don't know what automatic parallel. I think maybe optimizing anything. I mean, there is definitely work if you go to, for instance, the work of Höfler et al. They're trying to apply it, and many others, in fact, deep learning or machine learning tools to HPC, for instance, or to compiler building, and just doing smart decisions in compilers with deep learning, which, for instance, could be used to, you know, find, I don't know, SIMD parallelization strategies or something. But I think for anything, not particularly for deep learning. Does this answer your question?
Adesso mi collego io.
Okay.
Okay, so somebody spoke, Nicola, maybe. Okay, any more questions or curiosities? And if not, I would like to thank again very much the speakers, so Guido, Alberto, and Peter. And I would like again to congratulate with all the students of the 6th edition, because I think they did a great job. And this was a real pleasure. And I mean, seeing Peter is for me I'm really proud of what we managed to achieve. And Peter is one of examples of what how good HPC can be to and for our students. So I'm very happy that he was able to come and that he was willing to give us a talk. And I'd also like to congratulate all the students, because I think you did a very good choice. I mean, I personally think it's a very good choice if you like high performance computing. So congratulations again. If you want to turn on the cameras again, I would be very happy to actually virtually clap the hands to all the students that came in this year once again. So congratulations and thank you for staying so late for today. I mean, I know these are very difficult and are very tough online events, which don't actually give all the credit that you actually deserve and merit for the master in high performance computing. So I really wish I could have been live because it would have been much better. But I'm sure there will be times for this. In the meantime, you did a great job, and I think you did an excellent service to yourself and to your career, as Peter is a very good example of. So thank you very much for coming, and good luck to everyone.